So this is the start of Chapter 4, and we're going to be pulling from sections from Chapter 4 and Chapter 5 when we talk about factoring, because we tend to combine both the multiplying parts and the factoring parts into one section. Like before, we're going to be moving pretty fast over a review of stuff that you've done before. The first definition that comes from this, as we talk about the first two sections, is what a polynomial is and what we mean when we describe a polynomial. And in its most simplistic, a polynomial is a sum or difference of one or more than one monomial. One or so that raises the question, what is a monomial? Well, sometimes I find it good to just put down what a few examples of polynomials are before we just kind of get into the specifics of what we're calling a monomial. This is a polynomial, 7x squared plus 1. Here's another one, 16x to the fourth minus y to the second. Or if I have something like 7xy plus 49x. Those are all examples of binomials. They have two terms, but they are polynomials. And in math, when we talk about polynomials, we can even mean a monomial. 10x to the second is under the family of polynomials, even though it's a monomial. So don't get caught with the English of the difference between poly and mono. Polynomials like a family of things. Here's another one, 2 minus x squared y plus z to the third, x to the second, y to the fourth, minus 1/4 x cubed. And finally we have kind of a classic trinomial, x squared minus 5x plus 6. Those are all polynomials. Now when we specifically refer to a monomial, we think of monomial as a special case of a polynomial. I'm not going to be so specific as to ask you, is this a monomial or polynomial? That question will never come up. But we talk about a monomial, specifically a monomial, and the only example up above of a monomial was 10x to the second. A monomial is a product, and remember, product means multiplication, a product of variables and constants. And the only thing that's not really considered a monomial is the trivial case of 0. 0 is not considered a monomial because really when we talk about adding and subtracting to generate polynomials, we don't want to think about zeros having components. So 0 is not considered a monomial. So here's some examples of monomials. 7x to the third, 8x to the third y, the square root of 5 times xy. Notice how I wrote that with the square root of 5 as a coefficient, because if I talk about the square root of 5xy like that, that is not a monomial. That's not a product of variables and constants. That's a product of a constant and some square roots, and that's not what we're talking about. We don't want to be square rooting variables. The number 7 is a monomial. That's a product of variables and constants, because 7 would be the same as 7x to the 0 power. And I know I said 0 is not considered a monomial, but x to the 0 power is the same as the number 1. So that's fine. They don't need to be whole numbers, 14.2. They don't even need to be rational numbers. Pi plus 1 times x to the second. That's a constant times a variable raised to an exponent, so that would be fine. As is pi squared, because that's also just a constant. So those are monomials. We have another special case I'm not really going to define because it should be obvious as to what I'm talking about, but binomials. Typically when we talk about a binomial, we can talk about 7x plus 1. Sometimes we'll refer to 7 plus root 2 as a binomial, and sometimes we'll refer to it as a monomial. I know that sounds weird. 7 plus root 2 has a value that we can clearly describe, so it should be a monomial, but it's two pieces that can't be added, at least not in an exact way. So 7 plus root 2 will sometimes refer to as a binomial. So again, we're not going to get too caught up on the terms when it comes to whether it's a monomial, whether it's a binomial. What I want you to know is it's a polynomial. We have the special case of the trinomial that we talked about up above. Something like 8x squared plus 7x minus 1. That's a trinomial specifically written in descending order. So let's describe what we mean by descending ascending order. To talk about that, we have to talk about what the degree of a monomial and the degree of a polynomial are. If I describe, and these are descriptions, this is not a math thing that you're doing, it's just a description, the degree of a monomial is quite simply how many variables are present in that monomial. Now I'm even going to exchange that, how many variables or copies of the variable are present. Now, most of the time we think about just add up the exponents. So let's do a few examples and I'll show you some ways that it might try to trick you. Let's take some examples from up above. We had 7x to the second, we had 8x cubed y, we had the number 7. So if I would describe, and we set up like a little chart, here's the polynomial, actually this is the monomial, and then the degree. 7x to the second has 2 copies of the x variable, it has a degree of 2. 8x cubed y has 3 copies of the x variable and 1 copy of the y variable, it has a degree of 4. And the number 7 has 0 copies of any variable, it has a degree of 0. Again, if I put 0 down, don't be confused because 0 is not considered a monomial. So we don't describe the degree of something that is not a monomial. I'm going to just do a couple more. If I have 2xyz, that has a degree of 3. There's 1x, 1y, and 1z. So this isn't the hardest thing to think about. But what people sometimes get confused with is the degree of a monomial versus the degree of a true polynomial. Those of you who have ever played euchre, I like to think that the degree is a polynomial as which one of the monomials acts like the trump card. The degree of a polynomial is the same as the degree of the largest monomial. So I say, what is the largest degreed monomial? And that acts as a trump. Because as you're going to learn later with graphing, the behavior of whatever equation that you're looking at follows that of the largest degreed monomial. So if I talk about 8x to the third minus 4x y to the third plus 2x, that is a polynomial. It has 3 different monomials in it. The degree of the first monomial, 8x to the third, is 3. The degree of the second monomial, 4xy cubed, there's 1x and 3 y's, that's a degree of 4. And the last one is just a degree of 1. So the entire degree we describe as a degree of 4. This could become a quick process, especially with a polynomial in descending order, like 9x to the 5th minus 4x to the 4th plus x to the 3rd minus 2. The largest degreed object in here is the first monomial, and that has a degree of 5. So what we mean by descending order is we talk about descending degree. And descending order makes most sense when you're talking about the degree relative to one particular variable. You're going to see a lot of times how you might have something like 10x to the 4th plus 9x to the 3rd y plus 8x to the 2nd y squared plus 7x y cubed plus 6y to the 4th. And that has a degree of 4 regardless of which variable you look at. In fact, every single term or every single monomial present in there has the same degree. But it's descending order relative to the x's and it's ascending order relative to the y's. So you'll see some examples of that kind of throughout your time. Don't get too caught up and hung up on descending ascending order just yet, but you do need to know what the degree of a monomial is. So that's part 1. One little thing to point out is we have these interchangeable terms now. Monomial is the same thing as term. When we talk about like terms, we actually mean like monomials. So you've seen the word term before. Monomial is the same thing. Part 2, so 4.2, we're kind of doing two sections at one. 4.2 should be review, rules of exponents. So we've dealt with exponents in terms of talking about degree. Now we're going to deal with the operations you can do with monomials. I kind of label these rule 1, 2, and 3 because when we talk about some operations next semester, we're going to refer to these same rules in reverse. Rule number 1, when you multiply with the same base, the exponents get added. This is not terribly difficult to prove or demonstrate. For instance, if I have 7x cubed times 8x to the 5th, we have these commutative properties of multiplication that talk about the order not mattering of multiplication. So that would actually be the same thing as 7 times 8 times x 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 times x. And there are 8 of them now. There are 8 x's. 7 times 8 is 56, and x, there are 8 of them, so that's 8x, or x to the 8th power. Really, we simplify that process down greatly by just talking about when we multiply with the same base, we add the exponents. So I can jump directly to 56x to the 3 plus 5, or 56x to the 8th power. Some of the ways that we can test that on you guys is actually to use either variables or irrational numbers as the exponents. We're going to do a lot more of that next semester, but let me just give you an example. If I have 11x to the pi times 7x to the 2 pi, that's where you really have to think about the rule, because it's not immediately obvious. 11 times 7 is still 77, but x to the pi times x to the 2 pi is the same as x to the pi plus 2 pi, all as an exponent, which is 77x to the 3 pi. So multiply with the same base, add the exponent. Rule 2 is really just rule 1 in reverse. In some ways I've considered making it the same rule, but we keep them separate because we still think about multiplication and division as opposite operations rather than just opposite sides of the same coin. Divide with the same base means that you subtract the exponent. We've actually dealt with this probably just as much as the previous one. If I have 14y to the 5th over y to the 2nd, what's really happening is that that's 14 times y times y times y times y times y divided by y times y. And provided that, of course, that y is not equal to 0, y divided by itself is 1. So we can cancel two pairs of those y's out. I'm just left with 14y to the 3rd power. But of course it is far simpler to think about this as 14y to the 5th minus 2, or 14y to the 3rd power. We also see this when I have the larger exponent in the denominator. So if I have 100x y to the 5th over 7x to the 4th y, then my canceling is going to work where my x's are going to remain on the denominator with an x to the 4th, or sorry, an x to the 3rd, and my y is going to remain in the numerator with a y to the 4th. Finally, my last rule is the rule about raising a power to a power. If I raise an exponent to another exponent, we multiply the exponents. So let me do the case of the quantity negative 2x to the 2nd raised to the 4th power. Now what I'm actually doing is I'm saying negative 2x to the 2nd times itself 4 times. Sorry, it should be x to the 2nd in each of those cases. Which I can summarize as actually negative 2 to the 4th power, and then x to the 2nd to the 4th power, which is really x to the 2 times 4. There are 4 of these things. Negative 2 to the 4th power is 16, and x to the 2 times 4 is x to the 8th. It's worth noting that there is a distinction between the opposite of 3 squared versus the quantity negative 3 squared. I like to think about this as following order of operations. If I describe negative 3 squared without parentheses, what I really mean is the opposite of 3 squared, or the opposite of 9, which is not equal to positive 9. So Some problem types that we can do with this would be sort of like what I was describing before. We can take these things and multiply them and raise them, and so let's just do some examples. If I have x to the fourth raised to the n, I know that's a power of power, I can just make that x to the 4n. But let's say I have x to the, let's do a plus b, and I multiply that by x to the a minus b plus x squared. Now we have to keep track of what's going on. If I distribute this, x to the a plus b times x to the a minus b, I'm multiplying with the same base, but I'm adding the exponents. That's just going to be 2a. And then when I multiply this, that's going to be multiply the same base, add the exponents, a plus b plus 2. And that's as simple as it goes. I can also do this in multiple steps. Let's say I have y to the x power raised to the z times y to the z power raised to the x minus z. To keep this straight, let me cross my z's just to get that a little bit clearer. This is power of power, so this becomes y raised to the xz, and this becomes y raised to the xz minus z squared. And then when I multiply with the same base, I add the exponents, so I have y to the 2xz, then minus z squared. And that's as simple as that goes. Okay. Lastly, there are some tricks we can do. You're going to have some problems at the very end that talk about this, and I want to do an example. If I have 2 raised to the 5x, and I set that equal to 2 raised to the 6th times 2 to the 3x raised to the 4th power, and I want to solve for x. Well, I can do this with kind of not too much difficulty. What I need to do is simplify the right side. So I'm going to use power of powers here and change the 2 to the 3x to the 4th into 2 to the 12x. Then I'm going to change the right side into 2 to the 12x plus 6. And finally, I'm just going to look at the exponents and say, well, those two must be equal to each other. 5x must be the same as 12x plus 6. Which gives me negative 6 is equal to 7x, or x is equal to negative 7/6. Here's another application of this. I can do something like 5 times 25 to the 3n equals 5 to the n plus 1 raised to the 4th power. The trick here has to do with simplifying the left side. We're going to want to simplify both sides, but if I simplify the left side, I cannot multiply 5 times 25, because that's not 25. It's 25 raised to the 3n. What I can do is I can express 25 as 5 to the 2nd power. That's the trick. Everything else follows the rules. I can, on the right side, make that 5 to the 4n plus 4. Let's go back to the left side. This is 5 times power of powers, so this becomes 5 to the 6n. Then on the left side, this is 5 to the 1st times 5 to the 6n. This should be 5 to the 6n plus 1 equals 5 to the 4n plus 4. Now I can look at this and say that the exponents must be equal to each other. So 6n plus 1 equals 4n plus 4, or 2n is equal to 3, or n would be 3/2. I think that's enough for now. Good luck.